One of the common tasks in the Security Operations Center is for you to identify potential data loss from a specific traffic profiles and specific things and observables that you may obtain from the network. In my case, I'm actually sharing the StealthWatch dashboard, and you see that there's a specific source, the 10.201.3.149, which basically is being highlighted a few times of a potential data loss, for a potential data loss incident, right? So you see that there's some data that is being sent, but the maximum amount of bytes is 10 megs, right? And you see, a few other entries. One specifically highlights the user Ken, as you see, right? And if you click on the details, it will actually take you to this page where you see the security events for that specific transaction, right? So again, you'll see the source, the 10.201.3.149, and it says that security events is a suspected data loss, and it's because it's an indication that that host has uploaded an abnormal amount of data outside of the host. Now, again, this is just one example out of many that you can detect, potential exfiltration of traffic and sensitive information. There are other capabilities that help you detect the payloads of packets to see if there's, potentially credit card information, personal identifiable information, and so on, right? So this is just one example, but it's one of the, biggest tasks that you have in the Security Operations Center is to identify potential data loss from different traffic profiles and different traffic patterns.
Traditional IDS and IPS provide excellent application layer attack detection capabilities. However, they do have a weakness. For example, they cannot detect DDoS attacks where the attacker uses valid packets. IDS and IPS devices are optimized for signature-based or rule-based application layer attack detection. Another weakness is that these systems utilize specific signatures to identify malicious patterns. Yet, if a new threat appears on the network before a signature is created to identify the traffic, it could lead to false negatives. An attack for which there is no signature is called a zero-day attack. Although some IPS devices do offer anomaly-based capabilities, which are required to detect such attacks, they need extensive manual tuning and have a major risk of generating false positives. You can use more elaborate anomaly-based detection systems to mitigate DDoS attacks and zero-day outbreaks. Typically, an anomaly detection system monitors network traffic and alerts or reacts to any sudden increase in traffic and any other abnormalities. You can also use NetFlow as an anomaly detection tool. NetFlow is a Cisco proprietary protocol that provides detailed reporting and monitoring of IP traffic flows through a network device such as a router, switch, or a Cisco firewall. With anomaly-based analysis, a different practice keeps track of network traffic that diverges from the normal behavior patterns. This practice is called anomaly-based analysis. The limitation is that what is considered to be normal must be defined. Systems and applications whose behavior can be easily considered as normal could be classified as heuristic-based systems. However, sometimes it is challenging to classify a specific behavior as normal or abnormal based on different factors, which include negotiated protocols and ports, specific application changes, changes in the architecture of the network. A variation of this type of analysis is called profile-based detection. This allows systems to orchestrate their alarms on alerts in the way that other systems or end users interrelate on the network. Another kind of anomaly-based detection is protocol-based detection. This scheme is related to, but not to be confused with, the protocol decode method. The protocol-based detection technique depends on well-defined protocols as opposed to protocol decode method, which classifies as an anomaly any unpredicted value or configuration within a field in the respective protocol. For example, a buffer overflow can be detected when specific strings are identified within the payload of the inspected IP packets.
So let's go over what is cryptography. The actual word cryptography or cryptology comes from the Greek word kryptos, which actually means hidden secret. And cryptography is the study of the techniques actually used for encryption and secure communications, right? So there's another concept within cryptography called public key cryptography, right? Or public key infrastructure. That's what PKI stands for, right? And it has the concept of a private and a public key. The actual private key is the one that you actually keep, right? So that's actually private to you. The public key, you actually have it available to other users so they can actually decrypt or encrypt traffic to you, right? Or decrypt messages to you. And the main purpose of public key cryptography is actually to convert plain text to ciphertext, right? And a few things to actually remember here for the exam. The two concepts of keys, right? The private and the public key, and that the text that actually is not encrypted is referred to as plain text. The text that is actually encrypted, or the encrypted communication, is referred to as ciphertext. So again, the private key, you keep it to yourself. You do not share that key. If your private key is actually compromised, you actually have to revoke your initial key, right? And we're going to cover this when we go over detailed certificates later in the course. But the one that you actually share is the public key. A good example of a protocol that is actually used for email and file encryption is the PGP protocol or implementation, and it stands for pretty good privacy. And basically that has actually the concept of private and public keys. And again, you actually have public PGP servers. A very popular one is actually one hosted by MIT, the actual University of MIT, and where you can put your public key out there. So if somebody actually wants to send an email to you and encrypt an email to you, they will use your public key to encrypt it, and then you will use your private key to decrypt that message, because only you actually have that private key, right? So that means that if the user actually sends it to somebody else, of course that somebody else will not have your private key, so subsequently cannot decrypt your message. So that's one of the most simplistic ways of illustrating public key cryptography and PKI. A few of the benefits of PKI and cryptography is data confidentiality, right? So to make sure that data is actually encrypted, so nobody between the two entities actually can read that data. The other one is data integrity. That means that actually making sure that the data hasn't been changed. The other one is authentication, right? So authenticating that you are who you're supposed to be, and then of course that even the sender is who is actually supposed to be, right? And then the other one is non-repudiation as well, right? So the interpretation or the impersonation of somebody else. Now there's a few examples of where cryptography is actually used. One of the most basic examples is VPNs, virtual private networks. The other example is actually in e-commerce applications. So every time that you actually go to a e-commerce site, let's say, Amazon, and you buy something from there, you're actually using cryptography. And because your browser is encrypting data from your browser to their server, right? So to Amazon server. Every time that you actually go to your bank account, right? And, hopefully your bank has the ability to actually do encryption. You actually use protocols like HTTPS and TLS as well. Another example of cryptography is actually secure email transfer. And I mentioned to you PGP already, and there's other standards like SMIME and other type of encryptions that you actually can implement to encrypt email communications. Another example is actually credit card chips, right? So every time that now you buy something in your favorite store, you may actually be asked to use your card chip, right? So that is actually an example of the use of cryptography and encryption, because all that credit card transaction is actually being encrypted by the use of that actually chip, and that chip actually has some key material that is actually used and private information that is actually used to be able to identify, of course, your bank account or your credit card number in this case, but also authenticate and provide levels of encryption to actually be able to do that transaction. Now, there's another concept called cryptanalysis. And cryptanalysis is the study of how to actually crack encryption algorithms or their implementations on. So again, this is actually the ability to actually to try to determine how a bad guy will actually try to crack the encryptions and steal your data and the implementations, right? So there's a lot of studies actually being done on a regular basis on actually trying to see what encryption algorithms and hashing algorithms are more secure than the other ones. And we cover this in other lessons throughout this course. In public cryptography. And basically, a cipher is a set of rules which can actually be called an algorithm, right? They're also called algorithms. And basically, they're rules on how to perform encryption or decryption of packets or decryption of emails or, encryption or decryption of files as well. Now, there are hundreds of encryptions of algorithms actually available out there, right? And there are likely many more that are proprietary and used for special purposes, such as, government and national security. But some of the common methods that actually ciphers use as a whole is the method of substitution, another method called polyalphabetic, and a transposition as well, right? Now, there are also keys. And a key is a piece of information or parameter that actually specifies the output of a cryptographic algorithm. So you actually have a concept of a public and private key, just as we actually mentioned in the previous lesson. However, let's actually go over how that works in practice, right? So in this screen, I actually have two entities or two users. One is called Ben, and the other one is Pete, right? Typically, in examples of cryptography, you will hear, the word or the name Bob and Alice, right? So I wanted to be a little bit more creative and just change the names, and this is Ben and Pete. And then you actually may have an attacker in between, right? Let's just call that Eve. And Eve, and you will learn, what eavesdrop attacks are. Eve will actually try to eavesdrop the conversation between Ben and between Pete, right? There are many different ways on where you can encrypt traffic between these two entities. One is by actually using VPN, right? Things like a site-to-site VPN. You may actually have two different routers actually configured for IPsec. But in this case, it's actually looking at how Ben can actually send an encrypted email, right? Specifically using a protocol or implementation called Pretty Good Privacy, just as we mentioned before, so a PGP. Now, Ben will actually have a private and a public key. And also Pete will actually have a private and a public key. And Ben and Pete will actually change or share their public keys to each other. That means that for Ben to be able to actually encrypt an email to Pete, he will actually use his public key to encrypt that email. And then Pete will actually use his private key to decrypt that email, right? So that's actually the main purpose of the public and private keys. Again, you actually keep your private key all the time with you. If that actually key is actually compromised, you actually have to regenerate your key pair once again and revoke your keys. So that's the process of revocation. And you will learn about revocation once we actually cover digital certificates later in this course. Algorithms can operate some blocks of data at a time, or bits or bytes of data. And that's actually depending on the cipher or the type of cipher. And there are two main types of cipher: block ciphers and stream ciphers. A block cipher is a symmetric key, so that means the same key to encrypt and also to decrypt messages or transactions. And that operates on a group of bits called a block, right? Thus the word block cipher. Now, a block cipher encryption algorithm may take a 64-bit block of plain text, so again, traffic that hasn't been encrypted, or packets or data that hasn't been encrypted, and then generate a 64-bit block of ciphertext. And ciphertext is text that actually has been encrypted. And then with this type of encryption, the same key that is actually used to encrypt data is also used to decrypt that data. Now, these are some examples of symmetrical block cipher algorithms. The first one is the Advanced Encryption Standard, or AES. The second one is the Triple Digital Encryption Standard, or TRIPLE-DES. Its predecessor is actually the fourth one on the list, which is the Digital Encryption Standard. There's also Blowfish and also the International Data Encryption Algorithm, or IDEA. A stream cipher is a symmetric key cipher. That means, again, the same key to encrypt and decrypt data, where each bit of plain text data is to be encrypted one bit at a time. And that's actually done one bit at a time against the bits of the key stream. That's actually called the cipher digit stream. You must also know what are symmetric and asymmetric encryption algorithms. A symmetric encryption algorithm is also known as a symmetrical cipher, and that actually uses the same key to encrypt and decrypt the data. Basically, it's the same thing that we actually just covered a few minutes ago, right? So an example of this is actually two devices connected via VPN, both needing to actually exchange or key successfully to actually encrypt or decrypt data, between that VPN tunnel. And that's actually protected by a symmetric key encryption. So VPNs are typically using nowadays symmetric encryption algorithms, right? So that's where you saw examples like DES, TRIPLE-DES, AES, IDEA, and some others, right, that we mentioned before. Now let's go over what are asymmetric encryption algorithms, right? One of the characteristics of asymmetric algorithms is that they require more CPU processing power than symmetric algorithms. And asymmetric algorithms, however, are a lot more secure. A typical key length used in asymmetrical algorithms can be anywhere between 2048 bits to 4096 bits, right? So a key length that is shorter than 2048 is actually considered to be unreliable and not as secure as the longer key. So the longer the key, the more secure the algorithm will be. And some of the examples of asymmetric encryption algorithms include Diffie-Hellman key exchange protocols, RSA, El-Gamal, the digital signature algorithm, or DSA, and also elliptic curve cryptography, or ECC. So before we do that, let's see what is actually hashing. So hashing is a method used to verify data integrity, right? That means that you can verify the integrity of a file, you can verify the integrity of data being exchanged between two entities, or you can verify the integrity of a process or a program, right? A cryptographic hash function is the process that actually takes a block of data and then it creates a small fixed size hash values, right? It's a one-way function. That means that actually if two different computers take the same data and run the same hash function, they should get the same fixed size hash value. For example, perhaps a 12-bit long hash. And I'll demo this in a few minutes. Now, examples of hashing algorithms are the Message Digest 5 or MD5, which actually creates a 128-bit digest. It's actually less secure than the ones below. The Secure Hash algorithm, or SHA-1, it actually creates a 160-bit digest. And then the more secure is the second version of that, which is a Secure Hash algorithm, or SHA version 2, which actually include digest between 224 bits and 512 bits. So in this example, I actually have 3 files, right? File 1, file 2, and file 3. And as a matter of fact, if you actually see, file 1 in this case actually has the same bytes as file 3. So it's 32 of the size. And as a matter of fact, if we do a ls minus h to do a human, ls minus l and h, you can see actually 32 bytes in each, and then file 2 has 288 bytes. If we actually look at each of the files, so let's look at file 1. For example, the file context is, it's just self-explanatory. This is the contents of the file. That's what is actually in that file. If you look at file 2, the contents of the file is actually this. And if you see there's actually more data, subsequently you see the number of bytes actually increase. Now this is the particular fashioning here. File 3 is named file 3. However, if I open that file, you will see that the content is exactly the same as file 1. As a matter of fact, what I did before this demo is I actually copied file 1 to file 3. Now let's actually take a look at the actual hashing, right? So how to verify the integrity of those files. And you can actually have, most operating systems actually support hashing verification. In this case, I'm actually running on the Mac OS X device. This is very similar to a Linux environment as well. And there's a SHA-SUM utility, right, that you can actually use. And as a matter of fact, I'm actually just going to do the help in here. And basically, it prints or checks the checksums of a file or, a binary. And in this case, I'm actually going to use the 512 option of a SHA-2. So let's do this real quick. SHA-SUM minus a for algorithm, and then 512. I'm going to do it through all the files in this directory, so doing a wildcard. And here you actually see the different hashes for each of the files. So if you remember that the contents of file 1 and file 3 were the same, you actually see that the SHA-SUM calculated, or the hash sum calculated that is actually done in here, and the hexadecimal code in here is exactly the same as file 3, right? So again, file 2 was actually different, and subsequently you actually see it as a different output in here. So this is actually very important to know, especially whenever you're actually doing file integrity and file verification, and any other type of verification using hashing algorithms. And here, actually, I want to summarize what you learned in this lesson and in the previous lesson, right? So, encryption algorithms and hashing algorithms and what they're actually used for, right? So, first, starting from the left and the top left, symmetrical encryption algorithms. Remember that they actually use the same key for encrypting and decrypting data, and these are some of the examples of those algorithms. Then you have asymmetrical encryption algorithms, which use a public or a private key, right? So one key to encrypt data and another one actually used to decrypt, and some examples of those algorithms. Then we actually cover as well digital signatures, right? So this is actually done for the encryption of a hash using a private key, and then the decryption of a hash using the sender's public key, as we actually saw in the previous examples of PGP. Right. Also, you have the Diffie-Hellman key exchange, and of course the examples using IPsec, and encryption algorithms and hashing algorithms used for confidentiality, integrity, and authentication. Right. So here, self-explanatory. Some encryption algorithms that provide converting clear text to ciphertext increase the ability for you to actually protect the confidentiality of transactions and files. And these are some of the examples of the encryption algorithms to do that. And then for data integrity or for file integrity, which validates the data by comparing the hash values, just like we saw in the demo, these are the algorithms that actually are supported. And then, of course, you actually have algorithms for authentication and to verify the peer's identity.